So I'd like to start with the takeaway message up front. I think we're in a new space now in terms of the resources that are available, both electronic tools and some of the social supports are in place to begin to overcome the historical distance between formal schooling and the real world, and think about what it means to integrate across those two potential learning environments. And it's not going to be simple, and the transition is going to be led by the students primarily, but all the possibilities exist today. Now, to take advantage of these opportunities, it requires some rearranging of of ways that we approach education and our goals and how we think about the outcomes from education. And so we at the BioQUEST Curriculum Consortium place a lot of emphasis on the notion of understanding that is performance-based. Understanding is not something that sits in your head and that you can regurgitate on a page in response to a question. Understanding is the ability to do something. It's to perform in a particular context. And I like to use a graphic borrowed from John Seeley Brown, where he draws the distinction between the explicit knowledge, the sorts of things that can be written down and talked about that are hidden in our heads or stored in books, and the implicit knowledge that's the hidden part of the iceberg that's really much larger, which is how those things play out in communities of practice. How do we actually convert that textbook knowledge into being in the real world? And so when we're thinking about modern educational outcomes and the goals that we seek in designing new curricula or working with faculty to identify themselves professionally as educators, we're trying to push them towards a broader understanding a broader notion of understanding that gets them out of sort of traditional performance in explicit tasks. Now in the sciences, but in any discipline, we have a collection of special ways of operating that make up the practice of the discipline. And so this is a philosopher of science, Philip Kitcher, who talks about the language and the questions and the ways that problems are solved and the methods that are used to collect data and analyze data and the standards for judging other people's work. It works in biology, it works in the fine arts, it works in economics. Across the board, there are communities that have evolved norms of practice, and these are the kinds of goals that we need to keep in mind for students. And the only way to do that is to begin to transcend some of these traditional barriers between the school science and the real world learning environments. So the organization that I primarily affiliate with is the BioQUEST Curriculum Consortium. The BioQUEST Curriculum Consortium is a community of undergraduate biology educators that is sort of loosely affiliated users of modern technologies in classrooms and attempting to model these kinds of practices of engaging students in real scientific activities. And in terms of philosophically aligning ourselves with this notion of understanding as a performance activity, we think about our goals as these 3 Ps. And I highlighted part of our logo that has the 3 Ps in it, just in case anyone didn't get it. And of course there are 5 Ps, but just ignore that. Traditionally, science instruction has really focused on solving problems, right? We set students up with, if you're taking a physics class, there's a body of problems that you're likely to experience, and that those problems tend to be pre-posed for you, and the answers tend to be well-defined and known by someone. And what we're looking for in a more authentic practice is taking that very narrow school science notion and pushing it on both ends. What happens in a real scientific community? Well, the problems aren't posed, right? Identifying a real tractable problem and thinking about how you might go about answering it is a huge undertaking in science, and it's a huge outcome if you're able to do it. So what does a curriculum look like if students get experience posing problems, and how is that different from traditional curricula? Problem solving is pretty well worked out. Obviously there are ways to integrate more data and more tools and so forth. But we often assume that the answers are known, and we're checking against a known entity. Whereas in a more authentic scientific practice, we really want us to say, when are you done? When are you done? When do you know? Well, when you convince someone else that you know, right? When you've been able to marshal your evidence to convince the community to move on to a nuanced version of the next version of the problem. Or when you've stimulated someone to reanalyze their data because they sort of buy your point of view. So again, taking narrow current school definitions of scientific problem solving and pushing on both ends of it. Where do those problems come from, and how do we bring closure to problems? What do we do with solutions as we go out and persuade the broader community? So that's the sort of orientation part, teaching for understanding, thinking about disciplinary practice, and in the science context, we use this notion of 3 Ps. The lessons learned, or the things to be aware of that we've found that are leverage points that allow us to engage faculty around reform, educational reform, include things like the notion of a digital legacy. Now this has become relatively well known and commonly used term now that we have digital cameras and we're all collecting video information all the time. But it was originally developed very early on when some faculty in department in biology were collecting digital images with some of the first cameras attached to microscopes, and realized that they were having students do the same thing over and over. Go capture the image. Next year, the same students go capture the image, do the same thing. And so they started to collect those images and save them. And then next year, the students would look at the old images, maybe critique them, add something to the library. Or they would go in and they would say, you know, this image shows mitochondria in a particular position, but really, this one shows a cross-section much better. And so you can use digital legacies, now that we have the technical capacity to collect student work and organize it and make it accessible, to engage students in more realistic community practices. They're not responding to just the teacher's directive, but they're responding to existing work, a body of work that grows and develops over time. And they contribute to that work, so the audience is not just the teacher, but next year's students, and so forth.